we construct a power function with y factor 3. So the graph that we see here is of a power function with y factor 3, and it was constructed as follows. First, we picked an x value out here. We bisected the interval between 0 and this x value to get this x value. We bisected the interval from 0 to this x value to get this one. Bisected the interval from here to here to get this. From here to here to get this. So now we have a series of doubling x values. Now, we begin to construct our power function with factor 3. On our first attempt, we picked this point. This curve wasn't there at the time. We picked this point directly above this x value. And now we started tripling the y values as x doubles. So we have this x value, 2, 3, we triple it, we get this, at this x value we have this y value, which we go 2, 3 times, triple, to get a point here above the doubled x value. Then we triple this, we have 1, 2, 3 times this out here. At this, having doubled the x value to get a point up here. Now the curve didn't quite hit the point that I plotted, but that point wasn't all that accurate anyway. Okay, so in any case we get a curve that looks something like this, but this curve is way too thin, too narrow to really see the curvature, to really see the behavior of the curve. So we construct another graph, and this time we choose a point out here. Having chosen this point, we triple its value, 1, 2, 3 to get this value, and I think I came up a little short of tripling it, but yeah, we're doing this very approximately, but you get the idea. Then we triple this, 1, 2, 3 to get this. I think I came up short there as well, and I would have done better to use a compass, but I didn't have a compass wide enough to construct the graph on this board. Okay, now, in addition to that, we looked at how we would find the slope of a series of tangent lines tangent to this curve as a multiple of the slope of the first. So I took a point, well, I drew a tangent at this point. No, I'm sorry, it must have been at this point here. I drew a tangent line, this is it. And then at this point, I drew a tangent line. And at this point, approximately, I drew a tangent line. I then constructed a triangle between one point of the first tangent line and another. Then I did the same for the second tangent line using the same run. So the same run here. And then I did the same for the third tangent line once more using the same run. This allows me to get the slopes of this and this tangent line as a multiple of the slope of the first. Because the run being the same for all of them, the ratio of the rises will be the ratio of the slopes. If this rise is twice as big as this, then this rise divided by the run is equal to twice this rise divided by the run, since the run is the same in both cases. And if this rise is 3 times this rise, then this slope is 3 times this slope. So we estimate that. We find the slope of each tangent line as a multiple of the first. Right there's the rise of the first. The rise of the second is about 1.5 times the rise of the first. Now, you were asked to construct something of this nature, and you want to make your estimates a little more precise than mine, but you can do that, and you can actually construct those estimates using compass and straight edge. And then this third, it has a slope that's 1, 2, almost 3, I'd say 2.7 times the slope of the first. So if I wanted to construct a graph of the slopes, I could do that. I want my x-axis to go out about here. Now, the slope of each tangent line is going to be associated, the x value associated with that slope will be the x value of the point of tangency. Okay, the point of tangency here is here, so the x value would be down here. The point of tangency for the middle tangent line is pretty much about here, so we could mark an x value down here on this axis. And this tangent line, point of tangency, is around here, so we could mark this point, and then of course 0 is here. Now, the slope of this tangent line, well, it doesn't matter. This is an unscaled graph. We can associate with this x value any number we like. But now, if these numbers represent the slopes of these tangent lines, the slope of this tangent line is going to have to be about half again as big as the slope of this tangent line. So that means I've got to take this. If it doubles, it's here, so I'd say slope ought to be about here. And the slope of this is almost 3 times the slope at this point. Since we're graphing slopes, then the point that I put here is going to have to be about 3 times as high as this one. So that'd be 1, 2, 3, a little less than 3. And it appears that this graph would be concave upward from the estimates we've made here. Now, in fact, if you do this accurately for a power function with y factor 3, you do expect the graph to have an upward concave. Well, I'm sorry. If the y factor is 3, well, I'm not going to say whether you get an upward or downward concavity. This one seems to indicate upward, but we know that the slope at the origin has to be 0. We haven't actually proven that. So this point appears to be a little bit out of place. And it's not clear, maybe this point's the one that's out of place. It's not clear exactly what the slope graph should look like, but remember, I constructed this graph very roughly, didn't use compass and straight edge. If you were to construct it and construct the slope graph, you might come out with a different pattern of the slopes, because the slopes are pretty critically related, pretty critically dependent on the accuracy of the original graph. Now, a couple other things. You're asked to construct a power function with each of the above ratios. Here's ratio 3, or y ratios or y factors. And I should actually specify that, y factors. So maybe even cross out y ratios, although it would have the same meaning with the y factors. And a y factor, again, is the factor by which the y value changes when the x value doubles. Okay, there's more about exponential functions and so forth. I'll get to that in the next video clip.